Morning, everyone. Our next lesson in the permutation and combination unit is permutation word problems. And you'll notice right below the title, it says, let's try some trickier arrangements and more challenging questions. And that's what this lesson gives, is questions that are maybe slightly different, maybe slightly unique, maybe have a little bit of a twist to them. Okay? And we're going to look at 6 or 7 examples here today. So the first one says 6 members of the yearbook staff sit around a circular table. Kind of different. Let me explain why. How many different seating arrangements are there for this group of people? So the 6 people, that's not different at all. The word arrangements is not different. But what we're used to is arranging the 6 people in a lineup. And whether it was people, letters, books, teddy bears, anything like that, we're used to putting it in a lineup. And when you put it in a lineup, it's a classic 6 times 5 times 4 times 3 times 2 times 1. It's a classic 6 factorial or 720. And the reason that this is like this is that in a lineup, a definite start and a definite end. The reason that we have a definite start and a definite end is because we read, and we read from left to right. So in our case, we would see this particular position as the start and this particular position as the end. Just like if we were in the classroom and I made you line up at the front to the back, you would see the front as the start of the line and the back as the end of the line. There's logic. We have sort of an intuitive logic to a lineup. Where this question differs is that I still got 6 people, but what I'm doing with the 6 people is I'm seating the 6 people around a circular table. When we're dealing with a circle, this is a special case scenario, and it's not the same as a lineup. If I took a ring, which is in the shape of a circle, and I showed you my ring, when you see this ring, there's no definite start and there's no definite end. It's very, very different than a lineup. So when I look at this circular table, who's the starting person? Who's the ending person? I don't know. There is no definite start. So what has to happen? Because there is no definite start or end in a circle, we need to secure a person. Okay, so let me write this down. Because a circle has no definite start or end, a person must be secured. Let me give you an analogy. Everybody knows, all of you know that I wear hearing aids. And when I go to a big function that's in a hall, like a wedding or a luncheon or a school board type of function, because of my hearing aids and because of all the background noise, where I sit is really, really important. So if we have circular tables at any of these functions, I like to make sure that I sit down first and that I get my back, at my back is a wall, because at least if I'm backed up to a wall, I won't get any background noise behind me. But if I was sitting in another seat where there were all kinds of other tables around me, I would get a lot of background noise. So, you know, people that I work with, my family members, they all know that I want the chair that backs up to the wall. So I'm usually the secured person. I pick my seat first. So if I'm the secured person, that means that I'm not moving. I need that for important reasons. That means these other people, these 5 people, can move. So how many choices? 5. How many choices? 4. How many choices? 3. How many choices? 2. How many choices? 1. So the fact that this is a circular table rather than a table that's like a head table at a wedding, it changes it from a 6 factorial question to a 5 factorial question because you have to secure the person. So that's just something that you have to remember about circular situations. Okay, let's take a look at example 2. Find the number of seating arrangements of 8 basketball players on a bench. Okay, notice the difference here since we were talking about a circle versus on a bench. If either the one center or both of the 2 forwards must sit at the end with the coach. Okay, so let's think about this because this is mixing a whole bunch of concepts. If I put the coach at this end, and we'll think of like Coach Bigger or Coach Gallagher, and there are 8 chairs. And Coach Gallagher comes out right before the game and he says, so-and-so, whoever is the center, I want you to sit right beside me so that I can talk to you about strategy. Well, this situation is clearly the annoying child situation. The coach is telling one particular person exactly where he wants them to sit. Everybody else can move. Center has to stay put. Okay, but there's also this little word right here that we're familiar with, and we're familiar with the word or being addition. After halftime, Coach Gallagher comes out of the dressing room and he says to the kids, when we 1, 2, 3, 4, 5, 6, 7 get on the bench, I want the 2 players that play forward to sit beside me. That's what we have to work on. We have to work on that. I want the 2 forwards sitting beside me so that I can talk to them about strategy. So in essence, what you've done, we've had 1, 2, 3, 4, 5, 6, 7, 8, and now you've put the forwards together and they're not allowed to move. They're not allowed to move. Only these people are allowed to move. So I've got 6 factorial for the movable items. Okay, the 1, 2, 3, 4, 5, 6 boys that can move. But what's interesting about this is I could have the ordering of forward 1 and forward 2, or forward 2 and forward 1. So even though I've got my 2 forwards together, I've got to think about that order. And don't forget, even though they're together, they're not moving. They're being told where to sit. So it's an interesting question because it uses the or, it uses the annoying child, it uses the annoying boyfriend and girlfriend, but doesn't allow them to move. And we have to factor in order as well. It's a great question. So 5,040 plus 720 times 2, 5,040 plus 1,440 gives me 6,480. So just little different twists in all of these questions that make them a little bit more challenging and whatnot. How many arrangements can be made using all of the letters from the word swimmer if the S has to be after the W, the S always has to be after the W. Okay, hold on, let me think about this. 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. The S always has to travel after the W. So without the question using the word together, if the S has to always be after the W, it's insinuating then that this is a together question with particular order. So if the question was originally a 7 factorial, it's now become 1, the WS, 2, 3, 4, 5, 6 factorial. But what we can't forget, even though we've been focusing on the W and the S, what do I see right here that we learned in our previous lesson? Repeat M's. So 720 divided by 2 equals 360. So this is a together example without saying together and with also putting stipulations on the together. Okay, let's take a look at example 4. Little Lisa is playing with 4 blocks, each containing one of the letters from her name. Okay, so we've talked about this idea. In how many different ways can she spell her name wrong if she randomly arranges the blocks? This is kind of different because normally we're being asked in how many ways can you arrange these letters? That's a standard letter question. But this is asking in how many ways will they be arranged wrong? Okay, let me think about this. How many choices for the first spot? How many choices for the second spot? How many choices for the third spot? How many choices for the fourth spot? So if I was just asked, hey, can you take these 4 letters and arrange them in any way that you want? 24 ways to do that. I'm looking at how many of these 24 options are going to be wrong. Well, guess what? There's only one way out of the 24 to come up with L in the first position, I in the second position, S in the third position, and A in the last position. So there's only one way of spelling her name properly. So that means out of the 24 possibilities, 23 of them are wrong or incorrect spelling. Again, what's unique about this is really the little trickiness of the wording. We're reading that, having that pop out. Hopefully this helps. Okay, if you don't mind, can we flip over to our next example and take a peek at that? How many permutations of the word Martel can you have if the M and the A must be together? Now we've done a ton of togethers. So hold on, Martel has 1, 2, 3, 4, 5, 6 letters. 1, 2, 3, 4, 5, 6. None of them are repeating. M and the A together. So in a normal situation, if I just asked you to rearrange the letters in the word Martel, that would be a 6 factorial question because there's 6 letters. But because I'm putting the stipulation that the M and the A have to be together, we've changed it from a 6 factorial into a 1, 2, 3, 4, 5 factorial question. But what also has to be factored in is the order of the M and A. Don't forget, this is different than the swimmer. It doesn't say that the M and the A have to follow a certain order. They could go MA or they could go AM. Okay, so that doesn't seem too bad. That doesn't seem too bad at all. Let's take a look at the next one. How many different permutations of the word martell can be made if the M and the A can't be together? This is really different. This is our first time with the not. Cannot, must not, should not. We've always put things adjacent to each other, beside each other, together. That's been the way we've looked at it. This is a weird one. I don't know necessarily how to attack it right off the hop, but I'm going to give you a little technique, and my little technique is called reverse psychology. Now, this is not a technique that you're going to learn in university. Your profs are going to call this an indirect method. Everything to this point we've done very directly. Okay, we've looked at it logically, we've looked at how many choices, we've looked at order, we've done it very directly. The indirect method, or as Miss Martell calls it, reverse psychology, works indirectly. And I'm going to explain. Okay? Let me give you the formula, my own personal formula for reverse psychology. No restrictions. Minus opposite to what the question is asking. This is one of these formulas that you will have it memorized in words, okay? Now, no restrictions means just take a look at Martell and arrange the letters. So arrange letters of Martell. Well, if I was to arrange all of the letters in Martell, that would be 6, 5, 4, 3, 2, 1. Or 6 factorial, or 720. That's what no restrictions means. Now, opposite to the question, and that's why this is called the indirect method. Right now, they're telling you that M and A can't be together. So what's truly opposite to the question is that M and A are together, putting them together. This is similar, and the analogy that I use is sort of like a Romeo and Juliet scenario. Romeo and Juliet were told by both of their families that they can't be, they shouldn't be, it's absolutely, they can't be together. Yet they loved each other and they wanted to be together. So opposite to what the question is asking for, if the question is saying that, hey, those two letters can't be together, you put them together. So by putting them together, I just did that in part A. It was a 5 factorial times 2 factorial, or 240. So all of the options minus all of the options of them together will result in an answer of all of the options where M and A are not together. A lot of these questions, a lot of these indirect reverse psych questions, this is the best way to attack them, because you can't think of all of the options and do this in a direct manner. So hold on, let me reiterate. This 720 represents all of the different ways to move the letters in Martel around. This 240 represents all of the ways that you can rearrange the letters in a Martel with M and A being together. So no restrictions minus what's opposite to the question, all of the MAs together will give you all of the MAs not together. Takes a little bit of practice, but trust me, when you get this, it'll be like old hat. And the key element, the word that leads you into this, is this not. And there are some other words that lead us into it, but for right now, not is the primary one. Must sometimes is an indicator. At least sometimes is an indicator, not always. Not is the primary one, but both must and at least are sometimes indicators of using reverse psych. Okay, let's write that down. Reverse psych can also sometimes be used with must and at least. Okay. Let's take a look at example 6 now. A little bit tougher than example 5. How many ways can 7 different figurines be lined up on a shelf? Okay, we've done something like this with teddy bears, have we not? Lined up on a shelf. If the monkey and the elephant can't be side by side, here we go. Right away my brain is saying, okay, reverse psychology, indirect. Monkey and elephant can't be side by side. And the giraffe has to be at one of the ends. So you can see why this one's a little bit harder, because it's saying 2 elements can't be together, but it's imposing a restriction on another one of our figurines. So hold on, let's not get, psyched out about it. Let's start with our reverse psych formula. I like to write it out in words for myself. No restrictions. Minus opposite to the question. Okay, let's think about no restrictions. No restrictions would have everything in the question except the whole not element. Everything else in the question would be viable except the not. So if everything else in the question is viable, then that means I've got 7 figurines. 4, 5, 6, 7. And the giraffe has to be here or here. So if I'm placing the giraffe at the start, then that tells me that this isn't a 7 factorial question, but a 6 factorial question, because he's being told where to sit. But the fact that I can put him at the start or the end means that there's order, and I need to multiply that 6 factorial by 2 factorial, and that's because the order for the start or end for giraffe. Oops, sorry. So 6 factorial for the movable characters. Giraffe is sitting there, but then giraffe could also go at the end. Okay, alrighty. Now, opposite to the question. Well, if it's asking for the monkey and the elephant not to be together, opposite to the question puts monkey and elephant together. Okay, so hold on. Let me draw this out again. We have 1, 2, 3, 4, 5, 6, 7. I've got giraffe at one end. Don't know if he's at the other end. And monkey and elephant are now being put together because that's opposite to the question. So the question was originally a 7 factorial question. Okay. But now, with giraffe sitting here, it went to a 6 factorial question. But now with monkey and elephant being together, it's gone to a 1, a 2, a 3, a 4, a 5 factorial question times 2 factorial for giraffe at start or end, and then times another 2 factorial for order of monkey and elephant. It could go monkey elephant or elephant monkey. So again, question started off, if there were no restrictions whatsoever, 7 factorial question. Soon as I put giraffe being told where to sit, turns into a 6 factorial question times 2. Soon as I tell giraffe where to sit, but then put monkey and elephant together, don't forget, monkey and elephant can move into any of these 5 spots. So 1, 2, 3, 4, 5 factorial, 2 factorial for giraffe at start or end, 2 factorial for ME or EM. So let's do our math. 6 factorial times 2 is 720 times 2, which is 1440. 5 factorial is 120 times 2 times 2. 240, 480. Leaves me with a fantastic answer of 960. And that's our example 6 and final answer. Now, I've been wondering, I was thinking about it this morning. I've given you on your last quiz an algebraic factorial permutation question that was a little bit more challenging. So I thought, you know what, I'm going to throw one in the note today just so that you hear me go through it. Okay? So if you don't mind, now this isn't on your note, so you're going to have to take a moment, and I'm going to give you a moment to please copy this out. So let me give you a moment here to copy that out. This is going to be our last example for this lesson, but I think it's a worthy one, and I think it might be helpful for some of you to have me go through one of these with you, if you know what I mean. So let's take a moment and have you guys copy that out. And then we'll start. So when I'm looking at this question, I see I have a permutation of 2n minus 1. That's my n value. Choose 2, that's my r value. Plus another permutation of n, that's my n value. Choose 2, that's my r value. Equals another permutation of n. Choose 1. That's my r value. So anything highlighted in yellow is your n. Anything highlighted in green is your r. Now, right up here, I could just take a second and rewrite the formula for a permutation, just so we're aware of it. And I'm presuming most of you know that it's n factorial over n minus r factorial. So let's start slowly. I'm going to write slow and write big. So it's going to be n factorial all over n minus r factorial plus n factorial all over n minus r factorial equals n factorial over n minus r factorial. So in my first step, all I did was use my permutation formula. My next step, I noticed that this needs a little bit of cleanup, so I'm just going to rewrite. I'm not in a rush with these. Okay, you're usually talking 5, 6 marks, so you definitely don't want to rush and don't want to skip steps. Oops, my mistake. That should be an equals. Okay, now the next concept is to simplify this, clean this up, clean this up. And remember, when we were cleaning up factorials, we always were looking for where was the repetition going to start. So hold on, I'm going to start with this one. That's my n, n minus 1, n minus 2, I see the repetition starting. That's where the repetition, see the 2n minus 3? I'm seeing that repetition starting. So right away, anything at the 2n minus 3 point is going to cancel. And that'll just leave me with these two binomials. Let's keep going. n minus 1, n minus 2. I see the repetition starting at n minus 2. The repetition was starting. That's where I was going to be able to cancel. n minus 1. This cancels right away. So when the canceling has all taken place from your expansion, you're left with 2n minus 1 times 2n minus 2 plus n times n minus 1 equals n plus 23. Now you should be feeling good because this is just a matter of foiling, rainbowing, collecting like terms. So let's start with our foiling. First times first, 4n squared. Outside times outside, negative 4n. Inside times inside, negative 2n. Last times last, positive 2. Rainbow, n squared minus n. Nothing to do on the right. Okay, let's kind of clean this guy up. I'm going to bring all the n squareds together. Here's my n squareds. I'm going to bring all the n's together, and I'm actually even going to bring this guy over. And I'm going to bring all the numbers, actually bringing this guy over, together. The whole idea here is solving a quadratic, which is a grade 10 concept. So I simplified my factorials. I cleaned up by using FOIL and Rainbow. I continued to clean up by collecting like terms. And now I'm going to simplify that collection. 5n squared, negative 6, negative 7, negative 8n, minus 21 equals 0. Now, here's where things look a little bit different for you. When you've done most of these questions for me in the past, you've ended up with a trinomial, but it's been an easy or a simple trinomial that you can factor quickly. This is a tricky trinomial. So you've got no choices but to use the tricky trinomial technique. So hold on. What two numbers multiply to 5? No choice there. what two numbers multiply to 21? Well, I know we've got 1 and 21, and I know we've got 7 and 3. You never use the 1 and 21 as your first choice. You're always going to try your 7 and your 3. Okay, so what I'm trying to do is I'm trying to look for this number. So I do what they call out. I multiply, and that gives me 15. In gives me 7. Is there any way with 15 and 7 that I can result in a negative 8? 15 and 7, but I need a negative 8. Negative 15 plus 7, negative 15 plus 7 gives me negative 8. Factored beautifully. If you're nervous and you think, geez, I don't know whether I factored it properly, FOIL it back out and make sure you can get the previous line. Negative 15 plus 8 gives me negative 8. Now I'm going to take the contents of each of these brackets and I'm going to equate them to 0, and I'm going to solve. First one's easy. Next one takes a little bit of work. I'm going to bring the 7 over. I'm going to divide both sides by 5. And remember, we talked about this when we did our factorial lesson. Are these both legitimate answers? Well, I can look at this right away and say, absolutely, absolutely not. It's inadmissible. Now, why is it inadmissible? We can't have negative factorials, and we can't have fraction or rational factorials. So this particular option is being eliminated immediately on two accords. First, because it's a negative, and secondly, because it's a fraction. So I hope this example helps you with some of the tougher ones that you've been faced with. Thank you.